5 exponential and logarithmic models. Recognize the 5 most common types of models involving exponential and algebraic functions. Exponential growth and decay functions to model and solve real-life problems. Gaussian functions to model and solve real-life problems. So notice all these real-life problems, and that means word problems. Okay. So here are the 5 most common formulas that you'll be using solving real-life problems. And real-life problems typically use natural log, e's. Okay. Exponential growth, ae to the bx. Exponential decay, ae to the negative bx. Remember, a negative exponent is a reciprocal, right? So that's why when you have that negative, that's what makes it an exponential decay. The Gaussian model, ae to the negative x minus b raised to the 2 divided by c power. So you got 2 exponents there. That's a beautiful thing. Logistic growth model, a over 1 plus be to the negative rx. I was like, what is that letter? And logarithmic models, a plus b natural log of x, or a plus b log x, which is basically the same, just different bases. Take a look at what some of these look like. Exponential growth obviously goes up forever. Starts off slowly growing, and then as the growth increases, it increases even faster. Exponential decay starts off decaying rather quickly and then slows down. Gaussian model, what's that look like? Huh? Roller coaster? A bell curve? Okay, Gaussian model is going to look like a bell curve.
You know, I have learned this here. Each year event, we learn the same thing over again, they just throw something new.
It's typically how life goes.
But yeah, we did some of this, like algebra 1. Other than the other thing, just like the bell.
We have the logistic growth model, where it grows rapidly and then slows down. Natural logarithmic model and the common log model. Again, natural log model and common log model are basically the same. Major difference is the base on the log. That's it. We'll come back to these graphs in just a moment. You often gain insight into a situation modeled by an exponential or logarithmic function by identifying and interpreting the asymptotes. What the heck is an asymptote? It's an imaginary line that a graph approaches, right? Okay. And I'm going to eliminate the phrase "and doesn't cross." Okay. Now a vertical asymptote cannot be touched or crossed. Horizontal asymptote or a slant asymptote can be crossed, can be touched. In fact, it could be touched and crossed infinitely many times. But as x goes to negative infinity or x goes to positive infinity, the graph will get closer and closer and closer to that asymptote. Life's been a lie, I'm sorry. Okay. So assume that's a perfectly straight line. Okay, and assume that's an asymptote. I could have a graph that looks something like this. Isn't it getting closer to it? Okay. So basically, when you're talking, okay, when you're, let me change the phrasing. On a horizontal or slant asymptote, the asymptote describes the end behavior of the graph. So if this is a perfectly straight line, the graph that I drew is approaching this line, whatever it might be, y equals 1/4 x. So the graph is approaching that asymptote. It's getting closer. I know, but it's getting closer. Okay. Okay, so just, okay. So it says to identify the asymptote of the graphs of each of the previous functions. Okay, so we're going to look at the graphs again, and let's talk about asymptotes. The first one, exponential growth model. Does exponential growth model have an asymptote? Where? No. No. Yes. So an exponential growth model has a horizontal asymptote at x, oops, horizontal, y equals 0.
Why couldn't we just run this for asymptotes in the first place?
Okay. So E is just like 2.718, right? So the graph exponential growth model is y equals e to the x power. What can x be? Anything. That's why there's no vertical asymptote. X can be anything. Why is there an asymptote at y equals 0?
That's where it starts flattening out.
I've got e, which is 2.7 to the x power. If you make that exponent a negative number, it becomes a reciprocal. So it becomes 1 over e to the x power. So if I take 1 and divide it by a negative, infinitely large number, what will I get? Oh, it can't be negative. Well, the value of x is what it is. But when you take the reciprocal, so we have 1 over e to the x. So e to the x is getting infinitely large. What is 1 divided by an extremely large number? Can it ever be 0? That's why there's an asymptote there. Okay. Exponential decay. Do we have any horizontal or vertical asymptotes?
Horizontal asymptote also at y equals 0.
Okay. The Gaussian model, the bell curve.
Is there 2 horizontal asymptotes? There's one at 0 and one at, I think, 1.
No, just one. We have a horizontal asymptote at y equals 0. Does that graph go above 1? No, it's not going, well, whatever that value is, it's not going above that, whatever that value is, but that's not an asymptote. Okay. All right, more. Logistic growth model.
Has 2 asymptotes, 2 horizontal asymptotes.
Okay. We have 2 horizontal asymptotes. We have y equals 0 and y equals 3. Natural logarithmic model. Any asymptotes?
Vertical asymptote of 0. X equals 0.
Remember, on the previous ones we looked at, those were exponential. Exponential had horizontal asymptotes. If exponential and logarithmic are inverses of one another, what was a horizontal asymptote becomes a vertical asymptote. Okay. I'm not.
Do you not tell that we're reading backwards too? See the last slide?
Okay, moving on. Estimates of the amounts in billions of dollars of U.S. online advertising spending from 2011 to 2015 are shown in this table. Here's data. Okay, in 2011, 31.3 billion was spent. 2012, 36.8 billion was spent. So we're just looking at facts right now. Moving on. If we were to graph those points, looking at that graph, do those points appear to be a straight line?
Oh, no, they curve a little.
You see some curve? Okay, you see some curve, yes? Okay. So because of the curve, using this data, we could actually generate an equation. And they've given us this equation that S, the amount spent in billions of dollars, is equal to 9.3 e to the 0.1129 t, where t is between 11 and 15. Y'all okay with that?
Yeah.
That would be not a line of best fit, but an exponential function of best fit. Y'all good with that?
Yeah.
Okay. Oops. Need to slide down. We already did. So that equation is a model generated based on the data. Okay, it's just a model. I'm curious to see how close that model is if we plug the numbers in. So that's what we're about to do. So because we're going to plug 5 different numbers into that equation, are you going to type it 5 times? Are you going to use your y equals feature and go to your table? Okay. So type 9.3 e to the 0.1129 x into your y equals. And then let's go to the table and take a look at some things.
What are we putting in?
This goes into y1, except obviously we use x instead of t. On your table, what value do you see for 11? 30 what? Is that pretty close? Okay. For 12? Okay, pretty close. This one says 36.0.
Me too. Same. You don't get any.
No, I got, yeah, I put 114 on the
What? 32.
Why are you checking that? Right, 32.1.
How did you put it in the?
Okay, so 32.2. For 12, we get 36.0. For 13, we get, okay, 40.4. Okay, so you'll know how to use a calculator now. Great. Okay. All right. So how does the model compare to the numbers if we actually enter them in the equation? And they should be, right? Otherwise, it's not a good model. So based on the years from 2011, 2015, this fits the model. Can we use this to predict what's going to happen in the future? Yes. Would it be a good idea to use this model to predict the amount of spending in the year 2099? No. This would not be a good one. When you're using a prediction equation, you want to stay fairly close to the data that you know. Okay. Okay, so based on this, let's actually finish the problem. Compare the values, we've done that. According to this model, when will the amount of US online advertising spending reach 80 billion?
2019.
2019? 2020? Okay, let's do it algebraically. Where's the 80 go? Okay, so we have 80 equals 9.3 e to the 0.1129 t. You tell me what I need to do to solve this. Divide 9.3. What is 80 divided by 9.3? 8.6.
Mhm.
Okay, now, as far as writing it down versus doing the math, I'm going to write down 8.6. Doing the math going forward, I want to actually use the arrow up and actually use that number so that I'm not rounding it. Does that make sense? Okay. Equals e to the 0.1129 t. Next step, I want t by itself. Because base is e and e is the base of the natural log, we will take the natural log of both sides. That gives me natural log of 8.6 is equal to, don't do the math. Okay. Is equal to, when I take the natural log of e to that power, the e goes away, correct?
Yes.
0.1129 t. I want t by itself. Okay. T is equal to natural log of 8.6, but again, don't use 8.6, use that long, ugly decimal, divided by 0.1129. And you get t is about, it's going to be close to the same. 19 point. Okay, so how many years, in what year is 80 billion going to be reached? In the year 2019. Okay.
Yes.
Questions on this? It happens every once in a while.
It does.
Oh, no.
What do we know? They're not even close to being done?
Okay, moving on. Here's the first step of them solving it. They're showing some rounding and they're showing some of the math that I didn't actually work through. Moving on. They get about 19.1. So according to the data given to us, advertising spending will reach 80 billion in 2019. Yes. There's only second period in this period. I did second period on this today. Right. In living organic material, the ratio of the number of radioactive carbon isotopes, carbon-14, to the number of non-radioactive is about 1 to 10 to the 12th. When organic material dies, carbon-12 remains the same, but carbon-14 begins to decay with a half-life of 5,700 years. What's half-life mean? Okay. So I've got a certain amount of carbon-14. How long is it going to take for half of it to go away? 57,000 years? No. Yeah, 5,700 years for half of it to be gone. That's what half-life means, okay?
Why would they say that and not just its whole life?
Okay. Will the carbon-14 ever be gone?
No.
No. So it gets cut in half. And then what's left gets cut in half. So can you see it dropping a lot first year? Or the first 5,000 and then the next 5,000, the next 5,000? That gives you that exponential decay graph. Make sense, Caddy?
Yes.
Okay. Here's what the graph looks like. It says to estimate the age of dead organic material, scientists use the following formula, which denotes the ratio of carbon-14 to carbon-12 present at any time in years. There's the carbon dating model. R is the ratio based on the number of years. R is decreasing, correct? As it should with decay. We haven't had to do anything yet, but we're about to. The value of B in the exponential decay model, y equals AE to the negative BT, determines the decay of radioactive isotopes. For instance, to find out how much of the initial 10 grams of, I forgot what RA was, radium. To find out how much of an initial 10 grams of radium isotope with a half-life of 1,599 years is left after 500 years, substitute this information into the model. Let's go ahead and do this real quick. Yeah, I'll just talk through it. Okay. The equation is y equals ae to the negative bt. A represents the initial amount in this equation. Y indicates the amount after the time passed. B, we don't know. I know that the half-life is 1,599 years, but I don't know what B is. It's very important to calculate B to move forward with this problem. So to fill in everything, y is half of what we start with. So they actually wrote half of 10. So half of 10 is equal to 10 e to the negative b times 1599. Dividing both sides by 10 gives you 1/2 equals e to the negative 1,599 b. How do you get the exponent down? By taking the natural log of both sides. So that's where this next step comes in. So let's go here and then here. So natural log of 1/2 is equal to negative 1599b. Dividing both sides by negative 1599 gives us our b value. So b is negative natural log of 1/2 divided by 1,599. We can now use this formula to answer questions here. So using the value of b found above and the amount left is y equals 10 times e to the power of negative natural log of 1/2 divided by 1,599 times 500. All of that is your exponent. And this is all typed into your calculator. And you get 8.05 grams. Okay. It's just grabbing a formula and plugging numbers in. That's all it is. The Gaussian models. Gaussian model is y equals a times e raised to the negative x minus b squared divided by c power. Yes. When data fits this, it's called a normally distributed data. This is a bell-shaped curve. And we're going to look at graphing this in just a second. And obviously, you know why it's called a bell-shaped curve, right? Because it looks like a bell. Like a smashed Liberty Bell. So in 2011, the SAT math scores for high school graduates in the United States roughly followed the normally distributed distribution given by, and this is the equation. I'm going to write it out again because it's kind of hard to see. Y equals 0.0034. What does that represent? 0.0034. Something to kind of think about. It kind of represents your starting value, if you will. Okay, on the y value, on the y-axis. E to the negative x minus 514 squared, and that is divided by 27,378. That's not a 2, that's an exponent. Yeah. X is between 200 and 800. Why? What does 200, 800 represent? Okay, what's the maximum score you can get on math or verbal in the SAT? 800. What's the lowest number you can get?
200.
Okay. Turning it in? Yeah. Okay, let's take a look at this graph. second plus 7. Clear. Y equals to the fraction negative parentheses 27. Okay. What is our domain? We have a given domain, right? The function itself, the domain is all real numbers. But because this is a real life problem, the domain is going to be restricted to a real life domain. So I'm going to go to my window and I'm going to change the domain to be 200 to 800, counting by not ones, 50s. Will that work all right? Okay. We know it's a bell curve. We know bell curves are above the x-axis. So let's talk about the range. What do you want to be the bottom? Okay. Yes, 0, but normally I don't put 0 because I don't like the fact that it kind of almost chops off the axis. So I'm going to go -1. Okay. How high is this graph going to go? Remember, it goes like this. So there is some kind of a maximum. It's a bell curve. What is your A in this equation? Bad. So that's actually going to be my maximum. Okay. So I know it's not. So instead of being x min of -1 this time, I'm going to go ahead and leave it at 0. And I'm going to go up to 0.0035 and graph it. What's it look like? Does it look like a bell? I don't want to count by ones. I don't know what I want to count by. I guess I'll count by 0.0005. That looks good. What's the graph look like?
Oh, like this.
Okay. Does that look like a bell? Okay. Where does this value happen? That's what the question asks. Okay. X represents the math score, right?
Yes.
On a bell curve, where's the average going to be?
In the center.
Right in the middle. So if I can find the X value, that's going to tell me the average score on the SAT. How do I get that point?
You trace.
Okay. I would do calculate maximum. Calculate is right here. Second, calculate. I want to calculate the maximum, number 4. The maximum happens left bound. Am I to the left of the maximum right now?
Yes.
Enter. Right bound. Have I passed it? Enter. Guess. Am I close? Enter. What is the X value? What is that average score? 514.
Why would you do that and not just trace and find the number that?
Calculator is going to be more precise. Sometimes the calculator is going to jump quite a bit. Okay. So there's what the graph looked like. Half of the population is higher than 514. Half the population is lower than 514. Logistic growth. Some population initially have a rapid growth, followed by declining rate growth, as indicated by this graph. One model for describing this type of growth pattern is the logistic curve given by this function. Y is the population size and X is time. What would cause something to grow rapidly and then slow down?
It'd be like kind of like China, how they gave it to
Okay, they changed they made it so that you can't produce, you can't reproduce. Running out of resources, you run out of food, right? Okay. So there's different ways for growth to be going fast and then slow down. Bacteria, it's allowed to grow under ideal conditions. It's got food, it's got light, it's got everything it needs to thrive. And then we start removing those things. That's going to slow down the growth. Some things might adapt and continue to grow, but overall the growth is going to slow down. A growth curve is also called a sigmoidal curve. So there you go, sigmoidal. Got a college that's 5,000 students. One student goes on vacation, comes back with a Rona, a long-lasting flu virus. Rona was a long flu. There was a long time I never heard about anybody getting the flu. The spread of the virus is modeled by this equation. Y is the total number of students that are infected. The college will cancel classes when 40% of the students are sick. Oh, probably some time ago because we were making a prediction about 2019 that's in the past. Yeah. Yeah. Okay. First question, letter A. How many students are infected after 5 days? What do you do? Plug 5 in for T. Perfect. We can do that. Question B. After how many days will college cancel classes? Do you plug 0.04 in for T? 0.4 plugs into Y. 2,000. You're just going to start making up numbers. 40% of 5,000. Okay. So when will a school close down? When 40% of the students are sick. How many students represent 40% of the students? Of means multiply. So 0.4 times 5,000 is 2,000. Perfect. Slide this down some. Okay. So I'm going to do part B. I'm not going to worry about part A. I'm sure y'all can plug a number in and get an answer. Y, that is 2,000, equals 5,000 divided by 1 plus 4,999 e to the negative 0.8 t. The question wants to know, after how many days will classes be canceled? Solving for t. What should we do? No. Okay, so 2,000 times 1 plus 4,999 e to the negative 0.8 t equals 5,000. Next step. You could, but I wouldn't. Just divide by 2,000. 1 plus 4,999 e to the negative 0.8 t equals 2.5. Next step. Not yet. You got to get e by itself before you natural log. Subtract 1. 4,999. It's there. E to the negative 0.8 t equals 1.5. Next step. And you know what? Do that and just keep it. So I have e to the negative 0.8 t equals 1.5 over 4,999. And you know what? I'm just going to leave that alone. I'm going to keep it. It's ugly, I know, but the calculator is going to do this work for me anyway. Next step. Natural log of both sides. Taking the natural log of both sides gives me negative 0.8t equals the natural log of 1.5 over 4,999. By t is equal to natural log of 1.5 divided by 4,999, all divided by negative 0.8. T is about
This was one of the.
This is one of
T
those-
is about
This is always like the letter B.
T is approximately
10.41.
okay.
10.42.
Okay, which means what?
After 10 days.
The sick guy comes up with the flu. It's going to take 10 days for 2,000 people to have it.
You know,
School's closed.
this is one of those problems where you had the same equation, and then you just plug in random numbers and says the guessing check problem right now.
I know. 10.14.
That was fun.
Okay, I think there's one problem left, and that'll be it for this lesson.